So in other words, right under this, I want you to tell me what the derivative of that is. So here's the original function. Here's what it was, right? We wrote it all out, and then we took the derivative, and here it is. I want you to write what that derivative is using a sum. Sum. Okay, so create this. Make this happen with the series. Let's look for a pattern. 2c sub 2, x minus a to the first. 3c sub 3, x minus a to the second. 4c sub 4, x minus a to the third. So isn't this always some number, c sub same number, x minus a to the number minus 1? So n c sub n should work, x minus a to the n minus 1. Okay, let me try that. N times c sub n times x minus a to the n minus 1. That's what you said? Will that work? Where does, if this is going to be our formula, which I agree, that formula is going to work, where does your n have to start? Ron? Where does n have to start? You gotta wake up, go outside something. Seriously, this is one of the most critical things when you take derivatives of the power series, what's about to happen right here. Just go walk around, Ron. Is he all right? You all right? You want some ibuprofen? I brought some today. Okay, can we start at n equals 0 like the original one was? Try it. If n is 0, you get what? 0, okay. 0, right? Yes? But we would get, what, this to the negative 1? Which would be division by it, wouldn't it? And that might cause a problem. Imagine that this is negative 1. That would be down the denominator, right? And then what if x is a in that problem? You get division by 0. So we do not want to start it at 0. Start it at what? 1. Will 1 work? So if I plug 1 in here, what do I get? 1, c sub 1, x minus a to the 0, which would be 1. So what would that all be if I plug 1 in? The whole thing, what would it be? 1, c sub 1, all that's 1. So wouldn't that just be c sub 1? That's this, yes? Then if you plug in 2, you're going to get what? 2 c sub 2, x minus a to the 2 minus 1 is 1. Then 3 c sub 3. So that should work, right? But the index is now what? Starting at 1. Please, Ron, do not forget this. All right? It goes from n equals 0 to n equals 1. Does anybody else see what just happened? Look at this formula for a second. Look at this. I'm just going to rearrange something for you. This is multiplication, right? Does anybody else see this? Look. What really happened? I'm going to erase all this crap right here. Try and summarize, if somebody tells you to take the derivative of a power series, how you would do it.
Take the n down.
Take the n down, just like you did with power rule, right? Take the n down, and then subtract 1 from the n. What do you do to this constant? Nothing. That's how you take derivative of power series. But there's one additional kicker. You've got to change the index and start at 1. Otherwise, it's incorrect. Understand? All right.
Why didn't we do that in the first place?
I wanted you to see where it came from. If I just came up here and said this is true, you would probably agree with me, but now hopefully you see why it's true. I could have just given you the formula and saved us 10 minutes, but I'm not real big on formulas if we can figure out where they're coming from. I think it's more important to know where it's coming from. So, all right, so that's part 1. Yes?
You always change the n like forward 1? Like if it's 0?
If your original power series starts at 0, then this will go up 1. Yes.
Starts at 1.
If it's 1, it should go up to 2. But we're always going to try and get our series to start at 0 so that when we do this, it'll go to 1. All right, that was differentiation. What about integration? For integration, I'll just give you the formula. Okay, you can go derive it yourself if you want. If you have a function and you want to integrate it, so you want to integrate a function, then you can integrate its power series. So keep in mind that all we're doing is replacing f of x with its power series representation, right? Everything in this bracket is f of x. And going off of what we just did, what do you think would happen? This would become a sum n equals, what do you think? Do you think it's going to we're going to have to start at 1 or not? It actually turns out that with integration, it does not switch, okay? But everything else goes as you would think. And what is that you would think? What do you think happens to this? Stays. Okay, that's true. And then what do you think happens to the power? N plus 1. But what do we always have to do when we did antiderivatives? We had to divide by 1 over n plus 1. So it's going to be the same thing. I'm going to have 1 over n plus 1 x minus a to the n plus 1. All right, do you see the power rule there?
Yeah.
But it's integration, so plus c. All right, so let's do an example here. I'm going to do one that we already did because this will keep it short. What if I want to integrate 1 over 1 plus x to the 7th dx? We just did this problem a second ago, didn't we? Yes? So let me do it a slightly different way. I want to integrate the sum as n equals 0 to infinity of negative x to the 7th to the n dx. So where did this come from? Look back in your notes that you're taking right now. What is this? This is the power series representation of 1 over 1 plus x to the 7th. If we switch that to minus negative x to the 7th, and then rewrite it. And then, of course, we had an interval of convergence. We had to make sure that the absolute value of x was less than 1. Go back and look at that, all right? But instead of actually writing it out and doing it one by one, let's try and use the formula that I just gave you. So first, we need to rewrite this as negative 1 to the n, and then x to the 7n dx. So what did I do there? What did I do here? I just take that negative right out, and that's because this is always going to be my what? What's that going to be in my formula? That's my c sub n. And this part right here is my x minus a to the n, except we have 7n instead of n, don't we? But we will use the same exact power rule that we just used. Let's see if you can do it. What do you think the antiderivative will be? So equals, no more integral sign. I'm about to take the antiderivative, right? No more integral sign. The antiderivative of this series should be itself, the same sum. I'm not changing the index. Do y'all see that? But no more integral sign. The c sub n should not change. And then, I'm supposed to do like 1 over n plus 1, x to the n plus 1. But n for us here is really what? 7n. So this should be 1 over 7n plus 1, x to the 7n plus 1. And then plus some constant out here, right? plus some constant. Anyone have any issues with that? Everyone see what I did? I wonder if we can figure out what that constant is. Maybe. We'll deal with that in a minute. There was something else I want. Oh, can we check this to see if it works? If this gives us the right answer? Let n be 0, and what do you get? And I'm going to write out a first few of these. 0 here, we get what? 1, 1, 1. So just x to the 1. So what is it? You said 0. You said 1. Sorry. Negative 1 to the 0 is 1, 1, and then x to the 1. So just x. And then what's the next one going to be? Minus 1/8 x to the 8th. And then the next one will be plus 1. You're plugging in 2 now. 15th x to the 15th minus. Go back and look in your notes. Is that what we got when we integrated a little while ago? When we integrated it, that's what we had? Do you see we could have got the same thing using that formula instead? We only have 30 minutes. We haven't even... Okay. Y'all still hanging in there? Next example. I want us to rewrite this. I want us to rewrite this using a power series. Okay, a little timestamp here on my video. Okay, this is my little timestamp. Things are going to get a little strange right now, okay? Right? Things are about to get a little weird. Because this is what we need, okay? This is what we need. Yeah, the other one we did partial fractions, we were able to get this, weren't we? There's nothing you can do by just looking at that algebraically to rip it apart, can you? But you're recognizing something here. The derivative of that is something that's close to that, isn't it? Yes? So pay close attention here. The derivative of that is what? The derivative of f, I'm just thinking out loud here. Derivative of that is what? 1 over 1 plus x. That's what I'm thinking, right? That's a derivative. That means the antiderivative of this is that. Right? If the derivative of that is this, the antiderivative of that is this. So could I write this? That this is the antiderivative of that. You can't get it backwards. You can't tell me that this is equal to the derivative of this. Right? Understand the order of this? If I tell you to find the antiderivative of that, everyone's going to say, oh, the antiderivative of that is that, right? Plus c. But 1 over 1 plus x can be written as 1 over what? 1 minus negative x? Can't it? And 1 over 1 minus negative x can be rewritten as a power series. What power series can it be rewritten as? Integral still. Sum n equals 0 to infinity of negative x to the n dx. Backtrack. Rewrite that as a power series. I have no friggin' idea. But the antiderivative of this is this. But that is this, and this is a power series, and I know how to integrate power series with a formula. But I have to make this look like c sub n x minus a to the n. So I need to work with this still a little bit, don't I? What do I have to do? Peel out that -1, right? So that is equal to integral sum n equals 0 to infinity, -1 to the n, and then x to the n dx. Am I free to use the formula now? Yes? Use the formula, right? So am I going to write the integral sign again now? No, because I'm about to integrate. So I'm integrating a series, which means it's going to start at n equals.
1.
Are we integrating or differentiating? We're integrating, so you start at 0 still. To infinity. -1 to the n. Do I do anything with this? No, that's your c sub n. So nothing happens to that. But the x to the n is going to become 1 over n plus 1 x to the n plus 1 plus c. You got it?
Yes.
Does everyone understand that this series does not represent the antiderivative of that? This series represents that function. This is that, all right, within the radius of convergence. The way we got it was to use some information about the fact that the derivative of that was something we knew. So we didn't just integrate that, we just found what that was using a tricky backdoor in, if that makes sense. Now, this is correct. There's nothing wrong with that. But we need to get comfortable doing something because of where we're going with this. We always like our power series when we write them to be to the n power, don't we? X to the n. I mean, that's what a general power series always looked like, right? It was c sub n x minus a to the n, right? That's like the most general form. And it was sum n equals 0 to infinity. That's what a general power series looked like. And I think you asked me one time, does it have to be 1? Did you say that? Someone said that. Does this have to be 1 for a power series? Or maybe, I don't know who asked. But for a power series, this does not have to be 1 for it to still be a power series. All right? Or sorry, it doesn't have to be 0. It can start at 1 or 2 or 3. All right? But this we like. The thing with x in it to the n power. Right now, the thing that has x to it has n plus 1. Right? I'm about to make it be x to the n instead of x to the n plus 1. And what I'm going to do is what we call a shifting of the index. You ready? I want, right now, I'm going to shift my index. Shift index. When we say index, what I'm referring to is this index right here. This is our index. N equals 0 is the index where it starts to infinity. I'm going to shift it. My goal is to make this exponent be an n instead of an n plus 1. What would I have to replace n with to make that be an n, just an n, if I put it together? N minus 1. Does everyone agree if I replace that n with n minus 1, this will turn into n up here? So what I'm going to do right now is everywhere I see an n, I'm going to switch it to an n minus 1. And watch what happens. You ready? I'm going to rewrite the whole thing. Everywhere I see n becomes n minus 1. Sum. N minus 1 equals 0 to infinity. So that looks a little weird. We'll get to that in a second. -1 to the n minus 1. 1 over what? What's n minus 1 plus 1? N. X to the, what's n minus 1 plus 1? N. You see what I've done? Plus C. Now I need to resolve the index, correct. So what is this equivalent to? N is 1. Right, if I just add 1 to both sides of this, I get N is 1. So this becomes N equals 1. So if you take this power series, starting at 0, this is what it looks like, right? But if you shift the index, so change the index over to starting at 1 to infinity, it has the effect of converting x to the n plus 1 over to x to the n. And that is a skill you need to know how to do. No questions?
Is that why the derivative shifts to n equals 1?
The derivative switching to n equals 1 has to do with the fact that when you take the derivative of that first piece, the derivative is 0. Like if you write a power series, that first constant is 0. So when you try and regenerate that series, you don't want that piece there. So you move it by 1.
You did this in one of the homework videos as well.
Pardon?
You did this in one of the homework videos?
I did. I shifted. 8.5? Did I? Okay, good.
And we were just other conversion steps.
Okay, good.
Oh, okay, well, I haven't gone through it before yet.
All right. I think this is the last one we're going to have time for. Same instructions. I want us to rewrite this as a power series. Well, that'd be too easy, right? Yes.
Are we going to have trig functions in these?
You could. That's where I'm headed. Yes, we're headed there. Inverse trig functions. Anything, basically. But there's not enough time in this class. Just not enough time. We actually need like another 3 classes to get through this properly. I think. We need like another week.
Does it
But-
matter that we're not going to complete everything?
I think you've seen enough right now that you'll be okay. Yeah. All right, let's do this. If that were 1 minus x and that were it, we'd be okay, right? In the last problem, we saw natural log. What do we have? Natural log of 1 plus x, and we realized, hey, the derivative of that is something I know, right? This is the opposite. It's not the derivative of this that you know, it's the antiderivative of this that you know. So let me just, on the side, thinking out loud, what if I integrate 1 over 1 minus x to the second power? What if I did that real quick? Basic u substitution, maybe? U would be 1 minus x. Du would be negative dx. So you're off by a constant, aren't you? So rewriting this integral would become integral negative 1 over u squared du, which is the same as negative u to the negative 2 du. And what's the antiderivative of that? Power rule. So is it u to the negative 1? Because negative would come out, subtract 1. So that's just 1 over u, isn't it? But what's u? Minus x. So this is 1 over 1 minus x. All right. So let me recap. You're looking at this and you're like, man, this is all I know, right? It's all I'm ever comfortable with. Then we realize, wait a minute, hold on. That's the derivative of this. Why? Because the integral of this is this, right? So if I differentiate this, what should I get? That, right? differentiate this, I get that. I'll say it one more time. If I differentiate this, if I take the derivative, now I'm using what's called Leibniz notation, that's just telling everyone I'm about to take the derivative, treating x as my variable. If I take the derivative of this, that's equal to what? This. So I'm continuing this. This is equal to this, which is equal to the derivative of this. So this is all one string of equals. Yes? We all agree? But this I can rewrite as a power series. It's already there. Isn't that beautiful? So this derivative of this power series, n equals 0 to infinity of, this is a pretty clean one, right? X to the n. And how do you take the derivative of a power series? So I'm ready to take derivative. No more derivative symbol. What? N is 1. Why? Because that's what we said happens when you take derivative of a power series. That index shifts up 1. N is 1, but then for this, what? N comes out front, x to the n minus 1. Done. Within the radius of convergence, which I'm not even looking at the radius of convergence. Now, what if I asked you right now to make this power series have x to the n instead of x to the n minus 1? If I asked you to shift the index to make that x to the n, what would you do? You'd replace all n's with what? N plus 1s. And I'd like for you to do that. Let's replace all n's with n plus 1s. So sum n plus 1 equals 1 to infinity. I'm replacing this n with n plus 1. I'm replacing this n with n plus 1, which becomes x to the n, right? N plus 1 minus 1. And then the last thing is, what's this? N is 0. So you get that this is equal to, I'm just put it up here, this is equal to the sum n equals 0 to infinity of n plus 1 x times x to the n, as long as you're within the radius of convergence. It looks like I have time for more. I have time for one more. That only took us 5 minutes. All right. Here we go. You ready? We might go a little over on time. I hope everyone doesn't have anything planned after this class. I'd like to change that. Let's change this to x over 1 minus x, the entire quantity cubed. There's the original problem. Rewrite it as a power series. So first thing I'll do is this. Right? Okay. Do you see anything? You like this, right? You like the 1 minus x on the bottom, but the cubed is no good, and the x cubed on top is no good, right? Can't cube root. No, can't cube root. It's not. You're not gonna be able to cube root a series. So, how about this? Just follow me on this. That's what I need mostly from you right now, is just to follow everything I'm doing. Do you agree with that? Okay. Now, wait a minute. This. I think that's the derivative of something. Don't you? So let's try it real quick, thinking out loud. What if I integrated that? Isn't this the same problem we just did, except a cubed instead of a squared? So this would turn into integral negative 1 over u cubed, wouldn't it? Du, if I do the same substitution as earlier, which is integral negative u to the negative 3 du, which would be what? What is it? 1/2 u to the negative 2. Let's just check it. Negative 2 comes out, hits this, becomes negative 1. That's this. Subtract 1 from the power, you get negative 3. So do you agree that's the antiderivative? What was u? 1 over, or I'll write it this way. Write it this way. 1 over 2, 1 minus x squared. Yes? All right. All right, so I have to think through this again. This is this the derivative, or no, I'm trying to trick you. Is this the antiderivative of this? Am I tricking you? No, this is the antiderivative of that, right? Which means that that is the derivative of this almost, isn't it? Look, if I take the derivative of this, I should get that, shouldn't I? But there's this 2 here, this 1/2. Do you see that? So we have to somehow account for this. I need someone to help me in what I'm going to write on the next line. X cubed times. You just said that this is the derivative of what? This is the derivative of that down there? So I'm going to write this is the derivative of everything I see down here, right? 1 over 2, 1 minus x quantity squared. Now, are we okay with this? You sure? Sure? No issues with that? Okay. Now, I'm still continuing my equal sign. That is equal to, leaving that x cubed out here, actually, see that 2 on the bottom? Since it's a derivative, constants can come out, can't they? So how about if I do this? 1/2 x cubed times the derivative with respect to x of 1 over 1 minus x, that quantity squared. Yeah? Now we're hoping to turn this into a power series, aren't we? Yes? You understand what's about to happen? What is this? The previous problem. So we know what it took to turn that into a power series, didn't we? We did that in the, was it the previous problem? 2 previous problems, right? Or was it the previous? No, it was the previous problem. But from the previous problem, we already did the work, didn't we? We don't have to go back and redo this. What was this written as a power series? You should have it written down right there. Do you have it written? Who has it written? Anyone?
Summation
Let me
equals 0.
Let's see. Yes, and let's do the 0 one. Okay. So that was, and notice I'm still keeping the derivative, but this right here is the power series n equals 0 to infinity of n plus 1 times x to the n from previous problem. Right? So we know that our original function is this times the derivative of that, but that is this power series, and that we can take the derivative of. because this is x to the n, right? So we can do the power series now, the derivative. So 1/2 x cubed times, what is the derivative of this power series? So sum, n equals 1 to infinity. Do we do anything with this? No. But we do n down, x to the n minus 1. Nope. Nope, we're still not there yet. What I'd like to do now is take care of this x out here. This is x cubed, right? So since this sum involves n and not x, right? The thing that keeps changing is the n. The x is not affected by the n. This one, this is, right? This x to the n. I can pass this 1/2 x cubed into the sum, multiply it in. And when I multiply it in, I should get this. Sum n equals 1 to infinity of, let's see, the 1/2. I'll sit that in front of the n times n plus 1, which is these two just written backwards, and I put the 1/2 in front of them. And then I have x to the n minus 1 times x to the third power. And can you put those two together? Add the exponents. X to the n plus 2. So equals sum n equals 1 to infinity, 1/2 n plus 1, x to the n plus 2. That's your power series. But I'd like to have it as n power, not n plus 2. Can you give that to me as an n power instead of n plus 2 up here? You're going to have to replace all your n's with n what? Minus 2. So let's go replace all our n's with n minus 2's. Right here. Sum, if this becomes n minus 2, and I add 2, what do we get? 3 to infinity, 1/2. This n becomes what? N minus 2. This n becomes, or this n plus 1 becomes n minus 1. And then this becomes x to the n power. Still have time. That is the power series representation of that function.
So essentially what we want to try and do when we're solving these problems is try to find if we can integrate or differentiate part of it.
Yeah. Yeah. Let me show you the next example. I'm not going to do it, but let me show you the next problem that we are going to do next class. And this will be we're going to do this one. F of x equals x cubed minus 2x over 1 minus x, that quantity cubed. I don't know. Maybe we could do it right now. I don't know. I know it's almost time, right? I got 3 minutes. Just tell me if I can do this. Can I do that? Okay. Do you recognize the first part? What is that first one over there? That's the previous problem, isn't it? What did we get after all that work? What did we say that this series was? Sum n equals 3 to infinity, 1/2 n minus 1, times n x to the n. Wait, what was this one? N minus 2, n minus 1, right? N minus 2, n minus 1, x to the n. Yeah? This one, on the other hand, is a little more work. Because what we'll have to do is look at that one as negative 2x times 1 over 1 minus x cubed. Now, this right here, didn't we do that a minute ago? Yes? Can anyone tell me what that one was?
1 over 2.
So this is minus 2x, and it was sum? I want it as a series. What was this piece written as a power series? Let me see.
You got to pull out 1/2
Yeah.
from this.
It was this one right here.
And then
Yes, Sean.
you see what I mean? Like
Yeah.
that 1/2.
Okay, so this should turn out to be 1/2 on the outside, power series, n equals what?
Or, yeah, n equals 0 to infinity. N plus 1 times x to the n.
N plus 1? Was it?
Oh, dx.
Yeah, we need, hold on. Who else? You're confused? Anyone else? Everyone else is confused? Do you have it? Let me see it. Yeah, that's the one. That's the one. Okay. So you got to go back and look in your notes. It's this, and it's n was 1, right? And then it was n plus 1 times n, x to the n minus 1. Is that what you have? Yes? Sure? Double check it. Exactly? That's it?
I have that too.
Yes?
I was looking at
This is this. And then the 1/2 came out. And then this and this go away. I'm out of time. I can see you all running for the doors. If you got to go, you got to go. But I've come too far now. Can't turn back now. Okay, this, I still have an x out here. What will happen if I push that x into here? This will become together x to the what? N power. So we have that.
So we don't need to choose it?
Pardon me?
We don't need to choose the limit? The bound?
We're about to find out. There is a problem, though. We do have an issue that we need to deal with. You see that, though? They both are x to the n's? Double checking. X to the n. Yeah, this looks right. Okay. What's the problem? Anyone see what the problem is? They both have x to the n's. These c sub n's don't really matter. What's the problem? One of them starts at 3. The other one starts at 1. So you might be thinking to yourself, all right, let me just make these both start at 1. Or let's make these both start at 3. The problem is that if I try and tweak this to make it a 3, I'm going to change this. This x to the n is going to change. And I want these to be the same. Sorry?
Wasn't that n minus 1?
It was, but I brought that x in from the outside. There was an x on the outside I brought in. If you got to go, you got to go. Here's what I'm going to do. This right here minus. Let's let n be 1. If n is 1, what would I get? 2x. Right, if n is 1? What if n is 2? So plus, let n be 2. 6x squared? Yeah or no? Okay, then I can say n is 3, and then n is 4, and then n is 5. What if instead I say plus now the sum going from n equals 3 to infinity of n plus 1 times n x to the n? So what I essentially did was peeled off the first two of these. I peeled them off. Now this sum goes from 3 to infinity. You see it? And so when I put this out front and distribute my minus sign through, then, yeah, well I'll finish it. You get the gist of it. Now you could start to put it together.